Welcome to the Chapter 8, Part 1 video, where we will be looking at the reciprocal function. That's the function y equals 1 over x. We're going to look at how that relates to discontinuity and asymptotes. We've talked about asymptotes before for exponential and logarithmic functions, but we're going to look at this with what's called rational functions. And then we're going to review simplifying fractions and look at them, especially when there's polynomials in the numerator and denominator. So to get started, we're going to look at the reciprocal function, and that's y equals 1 over x. So go ahead and pause the video and put that into your calculator. In the top left button is the y equals, and then you're going to use the fraction 1 divided by x, x being the variable button, just like we've done before when graphing functions. Once you have that on your calculator, go ahead and resume the video. Okay, your graph should look like the one that I have on screen here, and that is the graph 1 over x. This graph is called the hyperbola or the reciprocal graph. Okay, and that's because in this shape there are two parts of the graph, and they are separated by these invisible lines called asymptotes. Now, when we look at asymptotes before, we said it's a value that the graph approaches but never touches, and we had a horizontal asymptote. Now we also have one that goes up and down, or a vertical asymptote that the graph approaches but never touches. So in general, when we have a graph of the reciprocal function, and we can perform all those transformations that we've talked about in previous lessons, where we multiply it by a number, add or subtract to x, add or subtract to y, all of those same transformations can be applied to this, and the asymptotes move with the function. Okay, so when we look at y equals a over x, for example, if you type in your calculator y equals 8 over x, you'll see that what happens to your graph is it looks like it stretches out, it gets taller. And then if you were to do something like y equals 8 over x plus 2, remember if it's grouped with x, it moves sideways. The plus 2 will make it move to the left by 2. What you'll see is that the graph is the same shape, but shifted over by 2 units to the left, and the asymptotes have moved with the graph. Okay, so that's the reciprocal function. All of the transformations we've seen before, we can apply. We're not going to go through all of them again, but keep in mind, shifting, stretching, all of that we've done before, we can apply to this function as well. You'll notice in the reciprocal function, those asymptotes created gaps in our graph. So I'm going to sketch the reciprocal graph here again. That's y equals 1 over x. And you'll see that there are no points with an x value of 0, right? If my x value is 0, I will never hit the graph. There's no point y with an x value of 0. That's because I cannot divide by 0. 1 over 0 is undefined, right? However, we also have this horizontal asymptote where the graph will never have a y value of 0, and that's because 1 divided by any number will never equal 0. Okay, so both of those are called discontinuities. It's a gap in our graph. We had to lift up our pencil in order to finish graphing. So you can think of a discontinuity as a place where you have to lift your pencil in order to finish graphing. There are 3 types of discontinuity. Okay, if we're looking at a point of discontinuity, we're looking at where does that graph not exist. So for our reciprocal function, the points of discontinuity are at x equals 0 and also at y equals 0. Okay, usually when we're talking about discontinuity, we're going to refer to the x value because we graph our functions over their domain or their x value, which is the independent variable. Okay, so discontinuity that we see in the reciprocal function is called a non-removable discontinuity. So let's start for y equals 1 over x. We have a non-removable discontinuity. And specifically, we've already named that this is called an asymptote. Okay. Another type of discontinuity is if we have something such as the step function or a piecewise function where we graph two pieces that don't quite connect. So if we graph something like this, where the pieces don't connect, but it is still a function, this would be y equals what's called the int function or the step function. This is called a non-removable jump discontinuity. Because while an asymptote creates a line that the graph approaches but never touches, here we don't have that happening. We have this point where the graph jumps, but it's not asymptotic. It's not approaching a value. Okay, and our last type of discontinuity is what's called removable discontinuity. And that's when we have a graph with just a hole in it, a line, and it could be a curve, and then it just has one point that's missing. And the reason that's called removable is because if I were to cancel out the value that makes that point removable, then it would be a complete function. It would have continuity, no discontinuity. So removable discontinuities are a hole or holes in the graph that can be canceled. And the way we cancel those out is if you look up at the notes box, we can have a factor in the numerator and denominator that reduce. Now, because that denominator still had a variable in it, there is a point of discontinuity. But once we reduce those, now there is no point of discontinuity. That's why it's called removable. We have canceled or removed that discontinuity. It is still a hole in the graph. We can create an equivalent function that doesn't have the hole. However, our original function did have a hole. So remember when we were doing function composition, sometimes we had to look at the process and not just the solution to find our restrictions in domain. This is exactly that same case where we reduced, but the restriction in the domain is still there. Okay. Let's take a look at some examples together. So we have three problems here, and for each of these, we are going to find the domain, the points of discontinuity, and then we're going to say if it's removable or non-removable, and if there are any x or y intercepts. Okay, so that's a lot of information we're getting just from a function. The first step for these is to notice that these are fractions, and in order to simplify a fraction, we need to factor. So our first step here is going to be to factor to see if we can simplify any of these fractions. If we can simplify them, that means the discontinuity is removable. And then I'll show you if we can't simplify it, how do we find the discontinuity? So in part A, we need to factor our denominator. The numerator can't be factored, so it stays the same. I need two numbers that multiply to 3 and add to -4. That's going to be -3 and -1. So we get x minus 3 times x minus 1. Now, my numerator is an x plus 3. The denominator has an x minus 3. That means those cannot reduce, okay? They cannot reduce because it's x plus 3 and x minus 3 are two completely different numbers. So this does not reduce, so it has non-removable discontinuity. Specifically, in order to find the discontinuity, we said it comes from the fact that we cannot divide by 0. So we need to say what numbers would create division by 0. And that also is easier to see in factored form. Just like when we were finding polynomials, we're going to set each factor equal to 0, but we're only concerned with the ones in the denominator. If my numerator is 0, that's okay. I can divide 0 by numbers. I just can't divide anything by 0. So to find the discontinuity, we set x minus 3 equals 0 and x minus 1 equals 0, which means that x is 3 and x is 1. So we have 2 points of non-removable discontinuity. Okay, here's 1, and we know they're non-removable because we could not simplify it. So my domain, it's going to be all of the numbers except for the ones that we just said we can't have. So our domain is all real numbers except 3 and 1. So I'm going to write it in interval notation from negative infinity to 3. Whoops, 1 is smaller than 3. From negative infinity to 1, and then from 1 to 3, and then from 3 to infinity. So all of the numbers except for 1 and 3. Okay, now to find the x-intercept, I want to know when y is 0. Okay, to find the y-intercept, I want to know when x is 0. Let's find the y-intercept first. The y-intercept when x is 0. So we have 0 plus 3 divided by 0 minus 3 times 0 minus 1. 3 over negative 3 times negative 1 makes a positive 3. So we get 0, 1. There is our y-intercept. To find the x-intercept, we set y equals to 0. Now, what value will give me a fraction that equals 0? We've talked about this before. We need the numerator to be 0. So to get our numerator to be 0, we set x plus 3 equal to 0, which means x is negative 3, giving us the point negative 3, 0. Okay, so let's make sure we answered our questions. We found the domain, we found the points of discontinuity, we found if they were removable or non-removable, and then we found the x and y intercepts. So that is part A. We're going to do the same thing for part B. For part B, first we want to factor. Our numerator cannot factor. Our denominator is a sum of squares, not a difference of squares, so we can't factor that either. What that means is that there's no value of x that will make my denominator negative, or rather 0, right? There's no value of x that can make my denominator 0. If you don't trust me, try it. Try a few values, okay? Denominator can never be 0. Therefore, no discontinuity. If you graph this, you'll see that the graph is, in fact, continuous. Okay, if there's no discontinuity, then it can't be removable or non-removable. That also means that our domain is going to be all real numbers. There were no points of discontinuity. Okay, we still want to find the x and y intercept. So let's find the y intercept first by setting x equal to 0. We get 0 minus 5 divided by 0 squared plus 1, which is negative 5, giving us the point 0, negative 5. And then let's find the x-intercept by setting y equal to 0. In order to get a fraction that equals 0, the numerator has to be 0. So we set x minus 5 equal to 0 to get that x equals 5, giving us the point 50. And then we go back and make sure we answered all the questions. We found the domain. There were no points of discontinuity, so they can't be removable or non-removable if they don't exist. And then we found the x and y intercepts. Okay, our last example, part C. Again, we want to factor. So I need a number that, or two numbers that multiply to negative 4 and add to negative 3. That's going to be negative 4 and positive 1. So that's x minus 4 times x plus 1 in the numerator. In the denominator, I have x minus 4. Those cancel out. What does that mean? That means it reduced. We have a removable discontinuity. Removable discontinuity at, where is it? Well, the denominator can't equal 0, so we said x minus 4 equals 0 when x is 4. That's where the discontinuity occurs. That means that my domain can be all numbers from negative infinity to infinity except 4. All the numbers except 4. Then we want to find our intercepts. To find the y-intercept, we set x equal to 0. I'm going to use factored form. You don't have to, but I think it's easier. Divided by 0 minus 4. So we have negative 4 times 1 is negative 4 over negative 4, which equals 1, giving us the 0.01. To find the x-intercept, we set y equal to 0, which means I need my numerator to be 0. That is x minus 4 is 0, although I also have a factor of x plus 1 equals 0. So I'm going to have two x-intercepts. X equals 4, giving me the 0, the point, and then x equals negative 1, giving me the point -1, 0. Two x-intercepts and a y-intercept. Did we answer all the questions? We found the domain, we found the points of discontinuity and said it is removable, and then we found the x and y-intercepts. There were two x-intercepts for a total of 3 intercepts. Okay, I have one more example, so let's take a look at that example where we are going to be finding the vertical asymptotes. I want you to give this a try and then we'll look at it together. Okay, so hopefully you were able to at least start this. A vertical asymptote is a non-removable discontinuity. So we're looking for the points of discontinuity that do not cancel out. Now, if we look at our function, none of the terms cancel out, none of the factors, I should say, cancel out. So we're looking for where does my denominator equal 0? X minus 2 is 0 when x is 2, so that's our first vertical asymptote. X minus 3 is 0 when x equals 3, so that's our second vertical asymptote. We have two vertical asymptotes here. Now, if you want to know how does this graph look, you can put it into your calculator. Make sure you group together your denominator. So if I was typing this into the calculator, I would do y1 equals parentheses x plus 1 divided by parentheses x minus 2 end parentheses open parentheses x minus 3 end parentheses and end parentheses. That will keep your denominator together. Okay, and if you do that, what you'll see is that we have this asymptotic graph, and you actually have to zoom out in order to see that there is a little piece between those two asymptotes that is in quadrant 4. So this is what the graph of that function looks like. By the end of this chapter, you will be able to create that graph. Okay, go ahead and pause it if you have more questions or need more time. Okay, so we talked about vertical asymptotes, and that comes from the factors in the denominator. That's what this box here says. Vertical asymptotes come from the factors in the denominator that would make the denominator 0, okay? The top box is talking about what's called a horizontal asymptote. Now, when we were looking at the graph of y equals 1 over x, we saw one of each. We saw a vertical asymptote on the y-axis. We also saw a horizontal asymptote on the x-axis. And what the horizontal asymptote does is it says what's happening to the end behavior of my graph. What's happening out towards positive and negative infinity. Okay, now there are 3 cases for this. And for all 3 cases, we're going to look at the degree of the numerator. So as a reminder, for degree, if I have x to the 5th, that's degree 5. If I have 7x to the 5th, the degree is still 5. So the degree comes from the biggest exponent. So when we're talking about horizontal asymptotes, we're going to be looking at the degree, the exponent, the biggest exponent in the numerator and in the denominator. Okay, now if the denominator, okay, is bigger, let's look at a fraction, something like x to the 7th. If the denominator is getting bigger and bigger and bigger, then my number, think about 1 over 100, 1 over 1,000, 1 over a million, they're getting smaller and smaller and smaller. So as the denominator gets bigger, the number gets smaller. If the numerator gets bigger, the number gets bigger, okay? So the degree of the numerator, we're going to call that m. So let me erase. Here we go. If we have x to the m divided by x to the n, and there could be other terms, but we're only looking at the biggest exponent. So m is our numerator, n is our denominator. Degree, if our numerator m is smaller than the denominator n, so the numerator smaller than the denominator means the denominator is getting bigger and bigger and bigger and bigger, so the number is approaching 0. This is what happens in the reciprocal function. Then we have what's called a horizontal asymptote at y equals 0. Just like our reciprocal function, that means our end behavior is just approaching the x-axis. If it's backwards, if the numerator is bigger than the denominator, then the number just gets bigger and bigger and bigger and bigger. It's approaching infinity. So we say no horizontal asymptote. Okay, our y values are approaching infinity, and that could be positive or negative infinity. If the degree is the same, so if the degree of the numerator equals the degree of the denominator, x cubed over x cubed, for example, then we look at their coefficients, a and b. If they don't have coefficients, that would be 1 and 1. And we could say the horizontal asymptote is the ratio of their coefficients. Okay, so first we look at the exponents. If the exponents match, then we look at the coefficients. If the exponents don't match, then we don't even care about the other terms. We don't care about the coefficients because the exponents determine the behavior of the graph. Okay, so we have vertical asymptotes come from when the denominator equals 0. Horizontal asymptotes come from the behavior of the graph, which we can see from the degree of the numerator and the denominator. Let's look at some examples. So in our first example, we want to find the horizontal asymptote of each rational function. So remember, we had 3 cases. Case 1 is if the denominator is bigger, then our asymptote is 0. Case 2 is if the numerator is bigger, then there's none. And case 3 is if they match, then we say A over B with the coefficients. So part A, we need to find what is the degree of the numerator? 1. What is the degree of the denominator? 1. They match, so we are in case 3. We need A over B. So now we need the coefficients. What's the coefficient of the numerator is 2. Coefficient of the denominator is 1. 2 over 1 equals 2. So we get y equals 2. Okay, let's look at example B. We need the degree of the numerator, which is 1. Degree of the denominator is 2. So the denominator is bigger. That means denominator is bigger. That means y equals 0. And then in part C, degree of the numerator is 2. Degree of the denominator is 1. The numerator is bigger. So there is no horizontal asymptote. There is some practice here on the last slide that you will do. If you need more help or if you have questions, make sure to schedule office hours and I will see you in class.